In this tutorial, we'll be examining the solar radiation heat flux to the ocean, and quantifying the amount that's received, and we'll look at the global distribution as well. The ocean is driven by the sun. The sun is responsible for all the primary heat flux components. We're going to be looking at the direct influence of the solar radiation. There is some heat received by the planet from internal heating, but it's quite small. The heat flux is quite small. There's also heating on the planet due to power plants and generation of heat by anthropogenic sources, direct generation of heat like your car engines, and but these are small compared to the sun. There are four key heat components that form the oceanic heat balance. Solar radiation, which is the topic of this discussion, obviously comes from the sun, and we have also known as shortwave radiation. We have another form of radiative heat flux, which is the long wave radiation, also known as backscatter. We have the evaporative heat flux, or latent heat flux, and we have the heat flux that's due to air-sea temperature differences that drives heat across the gradient, and that's known as a conductive or sensible heat flux. So that is those form a one-dimensional balance, and then the oceanic heat content is also distributed around the Earth by currents that carry warm water various places. For example, the Gulf Stream transports a very large amount of heat northward and allows places like England that are fairly high latitude to be quite warm. The solar radiation is a form of black body radiation. All bodies with a temperature greater than 0 Celsius give off radiation. And so this does not require a medium. Radiation can move directly through space as it does from the sun. The radiation that a body gives off is dependent on the temperature of the body. In fact, it's proportional to the temperature of the body to the fourth power. The greater the temperature of the body, the greater the radiative energy given off. The exact formula is given by the Stefan equation here. It's proportional to temperature of the fourth, where the constant of proportionality is the Stefan-Boltzmann constant, provided here. The spectrum of the radiation also varies with temperature, and here we have the wavelength in nanometers of the energy of the radiation in a power density curve. So we see here at higher temperatures, these are in Kelvin, the sun is about 5,500 Kelvin. At higher temperatures, the wavelengths are smaller, and since this moves at the speed of light, the frequencies are higher. At lower temperatures, as we move towards this black curve here at 3,500 Kelvin, you can see that the wavelength increases. So you have shorter wavelengths at higher temperatures, you have greater energy at higher temperatures, going as the temperature to the fourth power. When we look at our sun's specific spectrum, so again the sun's around 6,000 Kelvin, our sun's specific spectrum that it gives off is confined to a band roughly here, which corresponds to what we call infrared to ultraviolet radiation, which bracket the visible spectrum here. Now our eyes are tuned through evolution to be able to see the spectrum. That is radiation coming at us, and we define the wavelengths bands of those radiation as colors, and that's what we perceive in our mind. And then the human eye can see across this spectrum, and there of course are some animals like bumblebees and other animals that can see closer to this spectrum, and animals like snakes, reptiles, desert animals that can see more on this side. Also, this spectrum's, because the radiation provides energy to photosynthesis, plants are designed to receive energy specifically within this band for optimal growth. So that's where the sun's energy lies, and that's just a specific spectrum based on what the sun at its temperature and composition gives out. So we're talking about on the order of 0.2 micrometers, so in the hundreds of nanometers in terms of the wavelength of our solar radiation. How much radiation is coming out? So we measure radiative power as a density. It's power received per meter squared. So the sun is at a distance d from the planet, and obviously this picture is a bit exaggerated. The sun is far enough away such that the rays reach us essentially all parallel. If we take the Earth and cut it in half here, or conversely, if we just take a square meter panel right here and lay it normal to the sun's rays, the amount of sun that panel will receive is roughly 1,366 watts if it is a 1 by 1 meter panel. So for every meter squared of panel will receive 1,366 watts for panels that are facing normal to the sun. That 1,366 is not set in stone. There are some small variations on a fairly short time scale. There's the 11-year sunspot cycle here. This picture taken from the wiki page on solar radiation. And you can see here's this basically my lifetime here. We see these 11-year variations of the sunspot, which drive roughly plus or minus a half of a watt per meter squared variation in the solar radiation. There are also solar constant variations over very long time scales due to very small changes in the Earth's orbit and the Earth's inclination. These drive what are called Milankovitch cycles and are largely considered responsible for the periods of glaciation and very long scale time climate change. And those occur over a much longer time scales, hundreds of thousands of years. So keep in mind this number. This is known as S, but again, that is the solar density of radiation on a panel that is normal to the sun. Now the Earth is a sphere. We can think of it as a sphere. It's close to a sphere. So then the question is, what does an average meter squared of the Earth's surface feel? Whether it be this meter or this meter, what's the average over the entire surface of the Earth? Now, let me come back to the slide. If we examine this, we can consider this disk right here. So if we slice the Earth in half, like cutting an apple in half, and we consider the disk that's facing the sun and how much energy that receives, that disk will receive, the area of that disk is pi r squared, where capital R is the radius of the Earth. So the amount of energy that disk will receive, because it is normal to the sun's rays, it's going to receive the entire area times watts per meter squared will give us watts. This is the amount of energy that disk will receive at all times. But that energy has to be distributed over the surface of the planet. So keep in mind, some of the surface of the planet is receiving no sun if it's on the night side, and on the day side it is receiving sun. So naturally, the energy that's going to be received on the entire surface of the planet is going to be less than that received on a disk facing the sun, having an area equal to the cross-sectional area of the Earth. So the total area that's captured by the Earth is equal to the cross-section of the Earth times the solar constant, and that energy is available on average, to heat the surface of the planet. And the surface of a sphere is given by 4 pi r squared. That's the surface of the Earth, considering it a sphere. So that this much energy is available to heat this much surface. So on average, the Earth receives S over 4. So it gets cut down by a factor of 4 because it is spherical and because half of it is facing away from the sun. So that's on average. Of course, there are going to be variations latitudinally that depend on other factors, which we'll discuss in a moment. Now, not all the sun's energy reaches the surface of the Earth. Much of it is reflected directly by the atmosphere, or some is reflected directly by the atmosphere, some is directed off the clouds back into space, and some is directed back off the planet back into space. If you are an astronaut and you are on the space station and you can see the Earth, this implies that some radiation has reached the Earth and is directly reflected back. It's being reflected back in that spectrum, the sun's radiation spectrum, because your eyes can see it. And that means that the sun hasn't absorbed all that radiation. Otherwise, it would be black. So, because they can see it, that implies there is reflection back into space. And that reflection comes directly reflecting off the Earth, reflecting off the clouds, and reflecting off the atmosphere as a whole. That reflection we quantify using what's called the albedo. The albedo is essentially the fraction that is reflected or scattered of the solar radiation. And it varies over the planet. It depends on cloud cover. On the Earth, it depends on what's covering the local area. For example, snow has a high albedo. Ice has a high albedo, places where light reflects easily. The desert has a high albedo. Water has a relatively low albedo. Water likes to soak up solar radiation. So there are variations, depending if you're over water or if you're over land, and if that land is covered by snow, ice, or sand. And places that have persistent cloud cover on the planet are going to have, like some places in the tropics, are going to have a higher albedo because much of the sun's energy is reflected directly off the clouds back into outer space. So it never reaches the planet. It's not available for heating the planet. So these, you can see the variations here of this albedo, the highest being due to cloud cover here. And these kind of variations occur latitudinally due to ice coverage and cloud coverage primarily. On average, it's about 50%. You can think of an albedo. The amount of solar radiation that actually gets to the planet is about roughly 50%. But it does have strong latitudinal and seasonal and even longitudinal variation depending upon those factors I discussed. Now, thinking in terms of latitudinal or variations in the incident shortwave at the Earth, so on average we get S over 4. That's what we determine using simple arguments. At a particular location, you may experience more or less than that S over 4, depending upon key factors. One is this angle of incidence, and this has to do with what latitude you're at. Areas near the equator are going on average to receive greater than S over 4 solar radiation than those at the poles. Local absorption from the atmosphere, depending upon the composition of the atmosphere nearby, effects of clouds, etc., as we discussed. So the minimum, so you get the shortest path at this if the sun is directly normal to the land. So if the sun is directly overhead, you have the shortest path from the sun to you. You are most likely at that point to get a sunburn. That is because you have minimum absorption of the solar radiation coming down onto your body. You also have the greatest amount of solar radiation reaching a meter squared, available for the meter squared. At higher latitudes, or when the sun is lower on average in the sky, the sun has to traverse a longer path and therefore has larger absorption through the atmosphere. When we look at annual averages, you see the strongest effect here is the latitudinal variation. So we have a band of the strongest sun in the interior here, And you can see we're getting 250, something like that, watts per meter squared. 255 is roughly the peak that I'm seeing here, maybe a little bit higher. And again, so you have your S over 4, that's the average received on the planet, and then you have the albedo effects acting on to reduce that S over 4 further down to a peak of about 300 watts per meter squared, and when you get to the polar region, it's under 100 watts per meter squared because the sun is so low in the sky for at least half the year. So we have, these are again annual averages. So you have strong latitudinal variation, and you have some longitudinal variation. You can see that the contours tend to bend up or bend away from the equator as they approach the land. So the contours are coming up to produce higher solar radiation over the Earth, over the continents than over the ocean, because the ocean has a lot of evaporation. Evaporation makes clouds and reduces the solar radiation, whereas on land it tends to be on average sunnier. So you can see these contours bending away from the equator, implying at a given latitude you have stronger solar radiation over land than you do on ocean, generally speaking.